No, it's my great pleasure to welcome Professor Jack Sankey from McGill University. He's been a professor at McGill University for the past 4 years. And prior to that, he was a postdoc at Yale University, and in 2007, he got his PhD from Cornell University. And so I'd like to give a token of gratitude for coming down and giving the talk. Should I open it up if you want?
Nice. Good luck.
The floor is yours.
Well, thank you for inviting me down to Burlington to see UVM and get a book and give a sermon in this wonderful room. Forgive me if I'm weird or anything is incoherent. Just stop me and ask questions. I have a newborn. I have no sleep. And I drove a couple hours to get here, so yeah, just stop me and forgive any weirdness. So today, the thing I'm going to tell you about is a system that looks something like this, where we have two fixed mirrors that might be centimeter or fiber based, but they're facing each other. They form a thing called an optical cavity, and its job is to catch light, have it bounce maybe in our lab up to 300,000 times before it leaks out. And then whatever object you put inside of this cavity will have a 300,000 times, up to 300,000 times stronger interaction with each photon. And the object of choice for my lab is a floppy, 100 nanometer thick trampoline made out of silicon nitride that's just freestanding. So I'll give you an introduction to this kind of system and the fun stuff that you can do. And then I'll tell you about, we've basically been working for 3 years on fabricating these really delicate trampolines, and they do very well as force sensors. So we have our own nefarious plans with these things, but it is also a kind of a hammer looking for a nail, so if you have any ideas for what to do with 10 attonewtons sensitivity, let me know. And then I'll show you how this thing performs in a cavity. We sort of just started to make these measurements, and then what we're planning to do with these objects once we have the whole system up and running. And then I'm going to tell you about a thing that we came up with last year that I'm the most excited about that I've been about anything that I have access to in my career, and that is coupling the two totally disparate degrees of freedom nominally, coupling the light in the cavity, so that degree of freedom with the shape of the mechanical oscillation strongly. So that will be the last thing I tell you. And then I can drone on and on about other little projects that we have and other techniques that we're developing if you're interested. So just to give a motivation why mechanical systems, specifically micro electromechanical systems, they are everywhere in society. They serve as oscillators and timekeeping devices, accelerometers, and even as electronic filters. Just the mechanical resonance gives you an electronic filter at one frequency, for example. So you'll find them in things like watches, cell phones, and cell phone watches, laptops, cars and laptop cars, and other equipment that you might have around the house. And in the lab, also in science, these objects, mechanical systems, especially small ones, they play an integral role in many regions of applied and fundamental science. So, for example, my favorite is force sensing. The only way I know how to measure a force is to take a floppy object, apply force to it, and see how it deflects by maybe bouncing laser light off the back of it and seeing how it deflects. That's atomic force microscopy. And if you take a sharp enough tip and you drag it across a sample, you can, for example, image the forces exerted by individual atoms, which is happening down the hall from me in the Gruder lab. Or his old boss, I like this example a lot. He takes a nanoscale magnet, or I think he puts the sample on the cantilever, and then he has a nanoscale magnet, and he swings it across the thing so it sweeps through the field, and then applies he applies an RF coil that flips the nuclei in time with the motion, so you can be sensitive to a particular kind of nucleus and generate a three-dimensional picture of an object, such as a single mosaic virus with, you can't see this here, but it's 20 nanometer resolution. And so if you can make a better mechanical element, you can do really cool things. This is basically nano MRI. It's just like magnetic resonance imaging. Alternatively, you could take a mechanical object, and if it's a very good sensor, you could code it with receptors to a certain kind of molecule, and then you could just notice the frequency shift every time the molecules adsorb onto this object and sense masses this way. and people are starting to do this with single proton resolution. So that's why I like mechanical sensors. You can also use, at the same time, kilogram-scale mechanical objects to measure strains that are very sensitive. And you all have seen this data before, right? Yeah? Okay. I just want to say that I was talking about LIGO before it was cool. I have slides from LIGO years ago, but still, this blew my mind because they've been coming to my meetings and talking about this shaped object, this shaped data. And that's the raw data. That's ridiculous. But anyway, mechanical sensors play a role in detecting billion-year-old horrendously violent events from across the universe. And the field I'm in is called optomechanics, and the goal is to control these mechanical objects, and they can do it at all size scales using the radiation forces exerted by light. So here in Vermont, you've been hit by light before, you've been hit by photons. You don't probably remember it being a very profound experience. Even if you're at the equator and you held your hand up to the sun on the sunniest day at noon, the downward force from all of the photons landing on your hand would be about 10,000 times weaker than the buoyant force trying to float your hand, so it's not something you think about. But if you were to put your hand inside of a light-enhancing object such as an optical cavity, which I'll tell you the physics of in a minute, you can really enhance the strength of this force. And if you replace your hand with an optically pristine mechanical element that is lightweight, not a kilogram of meat, you will also enhance your ability to see these kind of forces or be limited by them or have your dynamics determined by them. And what's funny is you see all of these objects, gram-scale mirrors, even kilogram-scale mirrors have been laser cooled down to 200 phonons at LIGO. That's crazy. All the way down, membranes similar to mine, we're patterning them something like this, but smaller and lighter. All the way down, weird shapes like this, where the breathing motion is talking to light circulating on the inside rim, all the way down to ultra-cold atoms where you can really push them. Like one photon does a lot of damage. And most of these systems in the literature can be modeled, and most of the results, 99.9% of the results in the field, can be modeled and understood with this simple picture, where you have an optical cavity whose length is modulated by the mechanical element. So this is a fixed mirror. Here's a mirror that's on a spring that's free to mechanically oscillate. And the physics is identical to the physics of a slide guitar. So the basic idea is you have clamping points in a slide guitar that set the displacement to 0. And similarly, the mirrors here are clamping points for the electric field, so you have standing wave resonances that fit into this box. This is a 3-dimensional box, but you can think of it as a 1-dimensional box. So you have those resonances. In our case, we drive these resonances with an input laser that's at 200 terahertz. And a guitar, you can do the same thing by taking a tuning fork, hitting it, touching it to the base of the bridge. And then when you change the slide to the right frequency, the string will start to ring up and you can resonantly drive it. Same physics. And then once you have this thing populated full of light, every time the photon bounces off, it gives it that momentum kick, and you can get a radiation force from this. And similarly, you have an acoustic force that's trying to push the slide away. And by some freak coincidence, I plugged in numbers, and these are about the same orders of magnitude, which is funny. Which isn't to say that this is not interesting research, because guitars have been doing it for years. And also, I'll talk about a thing called finesse. In a mechanical system, its quality is determined by the Q factor, the quality factor, number of oscillations before it rings down. In optics, I talk about a thing called finesse, which is how many bounces the light makes, how many round trips before it escapes. So it tells you something about the transmission or losses in the cavity. Okay, so like I said, there's standing wave resonances. If we hold this frequency constant and then sweep this mirror length, or the position of the back mirror, you'll see that every half wavelength you come on resonance, and a whole bunch of power will build up inside this cavity. And for a few milliwatts input, so something like this, we actually end up with our best cavity having like 100 watts circulating inside. And that sounds ridiculous, and that is ridiculous. But at the same time, these are very nice mirrors with very low absorption, so they don't heat up much. Like, we don't even really notice it, just because the light that escapes the cavity is transmitted, or it doesn't matter. So that's fun. And then once you have that much light inside, you have the force from, this is 1 bajillion photons per second. That's, yeah, that's 1 bajillion. And if you add this all up, it's about a micronewton of radiation force under like high power conditions. And that's almost human scale. It's the weight of about 20 grains of salt in your hand. You'd almost measure it. You could push a paperclip in outer space, a centimeter, in about 2 seconds. So you can't sell this to the Department of Defense, because when the aliens attack, they will not use gram-scale ships with the world's best mirrors on the front. Nor is this a good way to repel them, because you have to actually hold the cavity on resonance. You have to move with it. So, or change your laser frequency as they move away. I'll let that go. So we'll make this arrow smaller. When there's high power in here, that's proportional to the radiation force. So we'll carry this picture with us. Next slide. If you look at one of these resonances, you can see almost all of the physics that you see in the literature so far. If you put the mechanical element right here, you're now in a situation where if the mechanical element swings to the right, the light will leak out of the cavity and you'll have less force pushing on it. And if it swings to the left, you'll have more force. And so this is this force versus displacement. The slope of that is a spring constant. So F equals minus Ks, right? So you get an optical spring from this, plus a DC force that will push on it always, and it will relax to a new equilibrium point. You can also get an anti-spring on the other side. And it's cool to point out a result that inspired a lot of what I'm telling you today from LIGO, where they actually took one of these cavities with a gram-scale mirror that's very easy to push around, and a big fat mirror that doesn't move as much. And they stuck in about 100 milliwatts of light, and they were able to use this spring to show that they could tune the frequency from 170 hertz. So this thing just, if you hit it, it would ring it like, ooh, it's probably, right? And then they turn on this laser, and they find that the frequency peak increases, the susceptibility, the frequency of the resonance goes up to something more like, you can hear that, which is 5 kilohertz. And what's funny about this is, think about an object this big and you hit it with a hammer and it goes, that's a very high frequency, right? And it turns out that this column of light was about 30% stiffer than a piece of diamond about the same length. But this is not to say that we're going to hold our spaceships together in the future with it, because it can only push, and it's also very brittle. So it's stiff, but it's very, very brittle. You have 20 micrograms of force, and it's gone. It's dead. Okay. So with this spring, you also have a lag in the restoring force. So as the mechanical element swings back and forth here, it'll take time for light in the cavity to respond, because just like on a harmonic oscillator, there's a cue. It takes a while to ring up and ring down. And so instead of just adiabatically following this for a finite frequency, you will have a hysteresis loop. So the light in the cavity will lag behind the motion. And then if you just integrate the work done by the force from the light on the mechanics, over one loop, the area of this loop is the total work done per cycle. And it actually does pump the motion of the mechanical element. This is exactly like, it's anti-damping, so injecting energy and keeping the oscillations going. It's identical to an engine where you time the explosion to occur while it's moving away. And that's exactly what's happening here. You have more force while you're moving away. And so people call it anti-damping or heating, laser heating, whatever, however you want to call it. If you put the mechanical object over on the other side of the resonance, you then have a minus sign in this loop, and that gives you damping. So, and what you're doing then is turning on a damping parameter without adding a lot of extra noise. And so people call this laser cooling for that reason. Because if you think about it, your mechanical element, every degree of freedom has a half kVt, right? Because it's attached to Earth. And the energy is transferred to Earth and back. through the dissipation. So it comes into balance, like if you hit this thing, it will ring down to some value, and then eventually it will balance. The rate of energy loss will be the same as the amount coming in from the thermal environment. And that is the fluctuation dissipation theorem, stated briefly, and it's responsible for the Brownian motion of the mirror. So you probably have not thought about this much, but a hot tuning fork, if you hold it up to your ear, you will hear it ringing at its natural frequency. It'll be like, right? And the reason for this is because the thermal environment is a hot white noise hiss, like, and then the mechanics has a susceptibility that really peaks at one frequency, just like a filter. Okay, and so people call this laser cooling because you have this nice little balance happening, and then you turn on the laser and you have a superhighway that you can suck energy out of the mechanics faster than it can come in from the thermal environment. And this is actually a colder object. Other degrees of freedom will also inject their energy, and that will get sucked out through the light. So the Earth is actually getting slowly colder. Very, very slowly colder. You can ask the question, how far can you take this laser cooling? And the answer is, you can take the mechanical temperature of this mechanical node arbitrarily close to zero, basically. And several groups with increasingly large sizes have started to laser cool these objects so that they are very close to the quantum mechanical ground state, where there's no more energy to give up anymore. It happens very quickly in cold atoms, as you can imagine. And then the first two were sort of this group and this group. This is a membrane drumhead coupled to the superconducting, the equivalent of an optical cavity in the superconducting microwaves. And now even my old group has recently started to see quantum effects in the motion of their millimeter scale membranes, which is very neat. Good. And you could imagine taking this idea of sensing forces even further to sort of the quantum regime, where if you have a cantilever that's very good, and you take a quantum system, and you somehow engineer force between these two things. So imagine you could have a spin here and a nanomagnet here. Then if this thing is in a superposition state, and this is not talking to the environment's not measuring it, so it's well isolated, then the force on this cantilever will be in a superposition. And if this thing remains pristine, you could bounce light off of the other side, and as long as you don't measure the light could be prepared into a superposition state. And so you can actually, there's proposals to transfer information from any degree of freedom, as long as you can engineer force, to mechanics and then to light. For long distance travel, you could use any wavelength you want, send it down a telecom fiber, and then you could imagine doing the reverse process over here, where the radiation force comes in a superposition because the light is either doing this or doing that. And that could transfer in a reverse way. So this is, a lot of the field is chasing this now, and they've started to do things like convert from microwaves to optical frequencies with good efficiencies, or different wavelengths converting through the mechanics. Okay. And so far, this hasn't been done. Oh, that would be the emitting entangle if you transfer the information. That's the sound of entanglement happening. Does anybody do quantum optics in this department? Yeah, so you haven't heard this, right? Because you haven't heard this happen. No? That's the noise. All right, so to summarize the field, you can control the frequency and damping. You can create and observe. I didn't really show you much of this, but you can observe quantum motion. And one group did a very cool thing at GILA, where they took one of these membranes and they made it so sensitive that it could hear the hiss from the individual arrival time of the photons. So the fact that the electromagnetic field is quantized results in something that sounds basically like raindrops and a heavy rain on the roof. They're able to see the mechanical motion respond to this. And then once you have that, you can do a thing called squeezing the light. You can have the mechanics start to become correlated with the quantum noise, and then the mechanics starts to modulate the light, which can then cause correlated fluctuations that cancel one quadrature of the other. For those of you that are interested in this, this is interesting to people like LIGO for getting below the standard quantum limit and measuring displacements. But again, I don't have time to go into that too much. So the field is relatively well developed, and so starting at McGill, my goal is to make a really nice micromechanical sensor and then enhance it somehow using laser light, like enhance its performance or provide new functionalities. So that will feed back into these kinds of applications, as well as classical sensing applications that we are thinking about doing. Okay, so at this point it's good. I'm kind of done with the intro part, and if you have any questions, or I see like a lot of baffled faces. I feel like I'm talking a mile a minute. No? Okay. All right. All right. So first, the next bullet is to talk about the low noise trampoline sensors we've made. When I got to McGill, we have a clean room, but we didn't have any process flows, so we had to develop this idea. It's a standard process flow, but we had to do it well. The idea is you start with a single crystal silicon wafer, coated with silicon nitride, 100 nanometers on the top and bottom. You can buy this for $100. It's this purple disc here. And then you do a thing called photolithography. Do you guys know what this is? Okay, so you spin on some plastic, you expose it with UV and a mask, and then you develop it like photolithography. You're left with plastic in this shape. And you put it into a reactive ion etch, just some chemical and plasma happening that eats away both the nitride and the resist. And you can transfer the pattern, and then we stick it in KOH and release it so that there's optical access from both sides. And what we're left with, here's a partial etch, and the final result looks something like that. So after much trial and error, the best device that we could make looks like this, where you have really macroscopic size, really weirdly large aspect ratios. So this is 3 millimeters across. The tethers are a few millimeters long. The central pad is this square, like modified square with pointy ends. And these are 2 micron wide tethers. And all of this is between 45 and 80 nanometers thick. Okay. And we can take this object, put it on its side inside of our vacuum chamber, 10 to the -6 torr, and bring a cleaved fiber end down. And if you zoom in here, you can measure the position of this object from the interference between the prompt reflection off the end of the fiber and the secondary reflection from the device. You can get very precise with this, sort of 100 femtometers per root hertz is no problem. Here's a picture of it in situ, sort of on a dusty Texas morning. The sun was coming in through the window really nicely. Or the camera was just underexposed and it came out yellow, but you can kind of see the little pads here. The resolution's too low, but you can kind of maybe convince yourself that you can see the tethers too. And the first thing to do is to just identify the mechanical modes. We did this by looking for places where there was a giant resonance with high Q and comparing to simulations from COMSOL, and they matched within 2%, which was ridiculous. I was not expecting better than 10% agreement. So we're pretty sure we know what the modes are, and then we can look at one of the modes. We know what shape it's bouncing, so we look at the center of mass motion of the central pad, and we can bring it up to large amplitude, so a few 10 nanometers-ish, let it bring down, and then watch what its time constant is to figure out the Q. And we find that this thing rings for 6 minutes in our vacuum chamber, which is a Q of 50 million. And that's awesome. So if you watch this thing ring down, you'll also see it land at the Brownian noise floor. So that's the thermal noise at the mechanical frequency. And you can, from just the mechanical frequency, which is 40 kilohertz, and the Q, which is 50 million, you can determine what you expect to see for the spectrum of this Brownian motion noise, and it matches very well with what we measured. This blue data is deceptively difficult to measure. It was like 40 hours of continuous measurement. It's weird. And if you divide this data, same data, just divided by the susceptibility of the mechanical element, you can infer the force noise from the system. And we find that it's down at 16 attonewtons per root hertz. And we could make this smaller by fitting them. Another group worked on a similar, almost identical shaped devices in parallel with us. And they found that they can even further increase the Q by making it thinner, but this is not helpful for our particular goal, so we stopped at this point. So that's encouraging. We want to put these objects into an optical cavity. Actually, I'll just say, like, this is the hammer looking for a nail. So if you can think of something that you want to measure at the attonewton level, or even in a cryostat, these things should have much higher force noise because the Q actually should go up that factor of 100. So let me know if you have an idea. And we also, so we have our own plans for these objects. We want to put them in an optical cavity and study how the mechanical properties of light impact its behavior. And so we stuck the trampoline into a cavity, and we can do the equivalent of a mechanical ring down of the cavity by sweeping the length through resonance faster than it can respond, and then measuring the light coming up. You can see it ringing down here. That's just an optical ring down. It tells us what is the hold time of the cavity and how much absorption the membrane is adding to it. And what we find is that, so here's just the resonant frequency as a function of the displacement of the trampoline. And we find that as we move the trampoline from a node of the standing wave in the cavity to an antinode, it goes, or the opposite, antinode to node, it goes up in frequency and then comes back down to the next antinode and goes up. This is just that the trampoline is a movable boundary condition. And so you can imagine solving the equations for the cavity modes, and this is what you get. And the other thing is, this is a good point to stop and say, this is the point at which, if you put the membrane here, or the trampoline here, you then have that classic picture of a cavity that looks like it's getting longer as a function of displacement. The frequency is going up and down as you move the trampoline back and forth. So we can do that kind of optomechanics. Good. Good. And then if we monitor as a function of where we are, we can look at the finesse of the cavity, so the quality of the cavity as a function of displacement, and we see it follows this funny curve here, and this red curve here is a lossless model with no real free parameters, so we don't see any evidence of absorption in this thing. It's compatible with a really nice high finesse cavity. A few 100,000 points we think would be possible. And why is this interesting? Well, it provides access to a new parameter regime. And one of the figures of merit in my field is the single photon cooperativity. That's fancy talk for this quantity, where this is really like, if you're familiar with atomic quantum optics, this will make some sense. This is the coupling rate between the light and the mechanics. This is the cavity's decay rate, and here's the mechanical decay rate. If this doesn't mean anything, don't worry about it. The point is we get a number 8. It's a unitless number, and it tells us that if we turn on a laser cooling beam at the level where there's an average of 1 photon in the cavity at a time, the damping parameter will increase by a factor of about 8. Okay? So this is a regime where like a really small amount of light will have a really profound influence over the motion. And so while we currently are trying to figure out how to lock our lasers to this object without having it ring up and get angry at us for an hour when we become unlocked. So we're working on that. We have a solution. I can tell you. Does anybody do feedback or locking in here? Laser stuff? Okay, well, if you know somebody, have them ask us. We'll give you parts list. We have a nice locking scheme. So that's under development. But now we're thinking of ideas like, you could imagine taking the mechanical object and telling it to ring, driving it, having it ring down, and then suddenly turning on this very weak amount of light, and the trajectories will diverge strongly based on whether there's light coming into the cavity or not. And so now we're wondering, if you're down at the level of a single photon, how will the quantized nature of light play a role? Like what will the individual arrival times of the photons mean? Or if we prepare the light in a squeezed state or a non-classical superposition state, a photon, not photon, what will happen? Because you get a strong divergence, like this small amount of light will really affect the trajectory that this object takes, even at large amplitudes. So you could imagine imparting some kind of big scale superposition. Yeah, so that's kind of the question. Another interesting parameter is if you move the object away from the usual kind of linear coupling to a position over here, you now have a situation where the cavity looks like it gets shorter no matter which way you move quadratically. Okay? And this is such an interesting topic that I will throw some equations at you. You can totally tune out now if you want, but it's not too bad. So if you've taken quantum mechanics, you know about, what is this? This is crowd physics? All physics? Okay. So if you've taken quantum mechanics, you may remember the harmonic oscillator looking like this, number operator, h bar omega. For the light field, it's the same thing, just like a guitar string, you have the frequency, the natural frequency, and the number of photons. And normally these are just two harmonic oscillators that are coupled, but now the frequency depends on position. So let's just ignore the fact that there are hats on everything and treat this as just a Taylor expansion. You have omega of x proportional to x squared. X looks like a plus a dagger. Square that thing, do your commutation relations, and then work at a limit where the cavity ring down time is so slow that the a dagger terms, which are fast oscillations at twice the frequency, go away. Okay, and then what you're left with is harmonic oscillator, and the interaction term here, which is just a bunch of constants times the two number operators. And this is a totally symmetric kind of coupling. You can read about it more in this paper. It's been known about for some time. What's neat is the number operator here commutes with the Hamiltonian, so if we find a way to measure the number, we won't destroy that quantum state. If it commutes with the Hamiltonian, it's a constant. Okay? And this is one way that we can imagine performing a non-demolition readout. So imagine group this n over here with this n so that it modifies the frequency. And the frequency will now be modified to have the number of phonons playing a role. And the way that I think about this is if you have a cavity frequency that's quadratic in displacement, a classical motionless object at zero temperature not moving will give you one cavity frequency. A quantum object, the 0 points mirror out of the position, will give you an average frequency that's a bit higher. Add a phonon to the membrane, and you'll see it spread out even a little bit more, and the frequency will just continue to go up like this. So these are the quantum harmonic oscillator states. And so you could imagine monitoring this frequency as a function of time, laser cooling to the ground state, and then just turning on this quadratic coupling and trying to look for jumps, discrete jumps as phonons leak in and out of the trampoline. So to get this to actually happen is difficult, as you can imagine. You need a low mechanical dissipation. I have that. Long cavity storage time, we have that. You need to make a strong quadratic coupling. I think I know how to make that. I can tell you about it later if you're interested. And low temperatures are good to prevent the fluctuations from injecting energy much faster. And in our case, we would need a much lighter, much floppier object in order to actually see this, to make the 0 point motion large enough to sample, to give us a big frequency shift. Okay. But there is something you can do with this that's much easier. And that's you laser cool to the ground state, you mechanically drive it to large amplitude so that there's an average number of phonons in the trampoline, and then you look for the fluctuations due to the fact that you're injecting energy and it's leaving at some average rate, but there's discrete arrivals and departures of the phonons. It's the equivalent of photon shot noise measurements. It's the noise on a laser. This is the noise on a driven mechanical system. And it scales like square root n, so you can get a better sensitivity. And we plugged in the numbers for our system, and we think signal to noise of 100 for a few nanometer drive will be totally possible with what we have already, which would be kind of neat. It's like a sort of demonstration that this thing is behaving quantum mechanically. Okay, so you could also take this symmetric coupling and group it the other way. So you bring this over here so that this guy is attached to the frequency of the mechanics. And you have now another kind of optical spring, where the light in the cavity is now really playing the role of potential energy. The energy of all the photons goes up if it swings left or right. And with this, we can do something like levitation. We would want this to be strong, and during my postdoc, I developed, like this is what I'm good at, is to use different modes of the cavity that have different shapes, make them interact with each other, and get really sharp, strong quadratic couplings so that you can make an efficient track. So why would I want to do this? Well, if I can take this high Q device and add an extra spring to it that has very little dissipation, so light has been predicted to be very quiet, just the shot noise is very small. Then I'll have a harmonic oscillator equation of motion looks like this, where you have your usual material parameters, your dissipation. And if you add a spring, you can analyze this very easily and show that the ring down time is proportional to the frequency. time is proportional to the frequency. This is a big deal if you can get it to work. And the reason is because not only are you making the mechanical element faster, you're also making it less coupled to the thermal environment. It doesn't leak to the environment doesn't inject force in it, so you can improve the performance of these objects by levitating them. And the ultimate limit is sort of a mechanical object that can ring for a month, but there's no way that we're going to reach that. It's a promising route to go. So some work has been done on this by the Caltech group. It's very encouraging. They did something very simple. They took a little pendulum like this, stuck it in a 15-watt circulating laser, which is ridiculous. This is a scary laser. It actually, over here at the high end, the thing melted. That's why they had to stop doing the experiment. But no cavities involved, just brute force, trap this thing with a dipole trap. And what they find is this motion is levitated, and its ring down time goes up as expected with the frequency. And then they hit a problem where they get a factor of 50 enhancement, so that's a fantastic result already. They didn't hit a very high Q because they started with a very bad mechanical element, but it's a nice demonstration of the concept. The reason that they eventually break down is this mode, which is levitated very strongly because it's moving in the light field, meets this mode, which is not moving in the light field. And these two things mix with each other. Like the normal modes that you started with are no longer the normal modes because you've added a weird boundary condition to this problem, so the normal modes are different. And as a result, they hybridize. The mechanics of this starts driving the violin string modes of these tethers. And those are still low, high damping, bad mechanical modes. And so it dies. You get sort of not great. And then it pops up, and then the next tether mode happens, and then it pops up again. It'll just bounce along in sort of a 50x improvement indefinitely. In our system, we could do that. It's not really like designed for it, but we could levitate, get a factor of 5-ish, limited by similar physics, the fact that this thing bends and these tethers start to wobble, cause dissipation, but we could get a Q of 100 million or something, which would be, and improve our force sensitivity a bit further. The way around this problem, we also did some work designing these devices. The way around this mixing with the tether modes is to destroy the mixing with a symmetry argument. So if you, instead of trapping the center of mass motion, you can make a device with two tethers and trap the torsional motion instead. And that by symmetry will not drive any of these tether modes. It will drive a very high frequency tether mode eventually, but that's at it won't happen immediately. And so if you turn on your trapping beam, you'll see the frequencies of, for example, this center of mass mode is blue. It goes up, hits an avoided crossing, the Q takes a dive, so this is the Q versus trap string. Same thing, it's a factor of about 50, dies, continues to bounce along at 50. Meanwhile, the torsional mode, which is really not exciting initially, continues to go up in Q. So we think we could get a factor of 1,000 or 1,500 without too much trouble in this system. And in order to get to this strong of a trap strength, you'll have to use these cavity-enhanced traps that I can talk if you're off the if you're interested. So we started making these things. I can show you slides about them if you're interested. They're not done yet. But if we started with a Q of 1 million, we could get a Q of 1 billion, which would be ridiculous. Okay, so I'm going to spend now some time on this last thing that I'm very excited about. But I thought I'd stop and see if there's any questions first. Oh. Okay. I think all of your eyes are open, so that's encouraging at least. All right, so changing topics. Let's imagine that we you could do this as a lab demo. Let's take a string and change the thickness of the rope and put it under tension. So this will make a thing called a phononic crystal, which just means it's a crystal in the sense that it's periodic. And the mass density depends periodically on position. It's under some tension. And so the speed of sound for transverse waves will be alternating. Right? And you all know how to do the wave equation and boundary conditions. You could find block solutions and figure this out. This is the thing that depends on X. Are you guys familiar with crystals and band gaps? Everybody? Okay, so I'll go through this quickly. If you grab this rope and shake it, you'll get traveling waves that go to infinity. You shake it faster, you get shorter wavelength traveling waves. You start to approach a wavelength comparable to the unit cell. And then you reach a point that looks like you start to see weird stuff happening. And then you reach a point like this, where it's no longer a moving wave, but a standing wave. And then as you shake it even faster, it decays exponentially. That's you entering the band gap. So you guys are probably familiar with this picture. Okay. Good. Where you have the frequency that you're shaking it, and the wave number goes imaginary in the band gap. And there's no states there. So our idea is to make a device like this, qualitatively like this, and then attach an optical spring to it. And you can add that to the wave equation as a spring constant density that adds a restoring force. And if you do this, this is really well understood physics. You know, this is not new, but what's neat about this is that you can control, you have a tunable defect in this crystal now, and you can control where the mode sits in the gap, and then change its mechanical, like the spatial extent of these mechanical oscillations. Okay, and so that was our idea, and so we just solved the problem. You know, you assume just this one pad is trapped, and do the boundary conditions. You can actually just analytically solve for the modes. And what we find is, yeah, as we increase the optical power, you'll get a frequency that goes, a mode with a frequency that follows this curve into the gap and back out again. It starts out fully extended, so an infinitely long standing wave in principle, like in theory, not in the lab, but in theory, at least not in my lab. And then as you turn on even an infinitesimal amount of light, it does give you some localization. Like this is sort of, it's the same physics as Anderson localization, for those of you familiar with this in 1D. Infinitesimal perturbation results in localized states, but it's a controlled single defect. Okay? And what's neat about this is, yeah, you can keep tuning it. You can localize it for realistic parameters down to, you know, a unit cell, and then it delocalizes into the shape of the upper band edge mode again. So the first neat thing is infinitesimal light in principle gives you a finite localization. This shouldn't be a square, but it goes like 1 over the power, the laser power that you're applying. And so we thought, well, let's see if we can make this in 2D. This physics would be very neat. And so please ask questions at this point. Like, I have not talked about this before, so I don't know what I'm doing. Okay, so I don't know what is confusing or what is annoyingly boring. So also raise your hand and say, like, that's annoyingly boring. Now move on. Okay, and make sure you speak for everybody. So we could make these devices. We have the fabrication protocol in principle to do this. You just pattern it into a unit cell that looks like this, so an object that looks something like this. Just many of these trampolines tethered together. And there's always a band gap in 2D for the out-of-plane motion. And when we do the simulation of trapping, we find the same qualitative behavior, and it matches our 1D model qualitatively very well. Semi-qualitatively, actually. We plugged in numbers from this model for the periodicity along this direction. So that's encouraging. Yeah, so we're using 100 nanometer thick nitride. You know, we've tried simulations with 10 micron pads, 100 micron pads, 500 micron pads. It all works. You could use a square or a hex lattice. So we started just making devices to see if we could do it, and it seems very promising. Same, using this existing fabrication technique, we can get sort of 4x4. We have a 6x6 device. The problem is if we try to make many, many tethers, a few of them will break. This is a very delicate system, and we think what's going on is, well, you start etching with KOH. Halfway through the etch, you have bubbles trapped underneath, and they push on the thing and break it. So we're learning how to sort of protect the front and the side. And, a lot of fabrication details that are probably not super interesting to you guys, but we're on our way, and we're kind of stumbling across this. And I made this typo, and I thought this was sort of appropriate for our level of understanding of the system so far. Okay, and so things we're going to try, what we're doing now is we're partially etching through the nitride, so we get almost all the way through with the violent KOH bubbles, and then we will use an HF, which is very gentle, to do the final release. And HF makes the surface high-quality optics, too. Okay, and initial results with this are, we think we have pinholes that are allowing holes through, like break holes, and minimum. So we're ordering thicker nitride. We're going to put the thing in a wafer chuck. We're going to ask for help at colloquia that we go to. So if you have any ideas, any fab knowledge, let me know. So this is sort of, hey, look at this thing that we could maybe do. We don't really know how to talk about this system yet. We have a few ideas about what to do with it. I'll tell you some in a minute. But we had to come up with some sort of figures of merit for this system, because people don't really, nobody's talking about this, so we don't really know what is important. So one of the figures of merit we came up with is, if you imagine a cavity trap with a single photon on average inside of it, what would be the localization length? It tells you sort of how efficient is this process at the quantum level. And it's very easy to plug in the numbers to this model. And we find that for a 10 micron long cavity, which we can make, and I'll show you how in a minute, we find the single photon localization length is something like 500 unit cells for this device that we simulated. And that's not absurd. It's 3 centimeters. So that's like chip scale. I was concerned when I started this calculation that we would say, oh yeah, we got this cool thing. It's really neat localization. But as soon as we plug in the numbers, it would be 4,000 kilometers would be the localization length, and good luck seeing that in a chip scale device. So, but this is very encouraging. It's sort of, you could think of a single photon mass now, effective mass of this, how much mass is oscillating. It's about 50 nanogram. So that's exciting. There's another figure of merit, which is how does the structure itself respond to a given trap, either a single photon or just any trap. So you could compare the situation where the mechanical structure has a certain amount of energy and it's distributed everywhere in this extended mode, and then you turn on, and then you compare with when the trap is on, all that energy would be localized to one region, and so the amplitude would change at the center. You could say, what is the ratio of these two things as a function of the crystal size for a given amount of localization length, so for a given trap. And what we find with a simple calculation in the weak light limit is this formula, which is not super obvious, but if you imagine the crystal, for example, being larger than the localization length, you find a square root n scaling. So this is a funny thing. If you make the crystal larger and more massive, you do better in terms of the response to the light. So what you're doing here, if you're interested, is the light is coupling to a continuum of modes in the same exact way. And these modes conspire to give you a sort of interferometric enhancement of the motion at one location. And this is really counterintuitive. Usually when you make something larger, you expect a weaker coupling because light bouncing off of it, it's a heavier mass, it's not going to respond as much. So this is exciting for us. Even if you make the crystal small, so you make it smaller than the localization length, you can Taylor expand this thing again, and you find a fractional change in the amplitude that is still scaling up with the size of the crystal. So as you make the crystal larger, initially it's linearly increasing. And for the devices that I showed you a moment ago, we think we can get sort of 10% scale for a single photon trap in the same trap that I was showing you, which is kind of neat because, well, I'll show you examples in a sec. So it's a very big response. And what's neat about this is you could be driving the mechanics to very large amplitude here. There's no reason why it couldn't, other than the device breaking, be large motion, big superposition you could achieve if there was some way to create a superposition of, say, trapped and not trapped, or photon and not photon, or something like that. So we don't think that that will be possible. There's a few reasons why not. But we have ideas about where to sniff around and look for cool ideas where you, instead of injecting classical light, you inject something interesting into the cavity and try to map that onto the motion in this really strange way. So I have a list of half-baked ideas, and they get increasingly baked or decreasingly baked. If you make the bread analogy versus the illicit substance analogy, I'll leave that up to you. But this is not so half-baked. You will get a Q enhancement from the partial levitation, And then you'll also be making a mechanical node that is isolated from the boundaries. It localizes, it doesn't shake the boundaries, it doesn't radiate energy as easily. So that will be interesting just by itself. And then you could even tune the mechanical interaction with those clamped boundaries to learn something fundamental about dissipation. People currently make many, many devices that are nominally the same and then study their cues in different modes. But here we could actually take a single device and smoothly tune the amount of interaction between the mode, the amount of bending versus the amount of clamping in the mechanical mode, and learn something about dissipation. So that's sort of a classical, fun direction to go that's pretty straightforward. You can also imagine coupling cavities to each other by like changing the lead in this cavity. You change how much the mechanical node interacts at this cavity, maybe transferring information through the mechanics in a weird way that people haven't thought of. This is where it starts getting very half-baked. You can have a qubit here with a magnet there and start thinking about weird kinds of, well, you can tune the interaction with between the mode and the qubit. This is an open question, this kind of stuff. So don't take it as me planning to do this. But people at my last conference kept coming up and saying these things as well. And then we would just point to a poster and be like, yeah, but what do you actually do? And so that's kind of where we're at right now. And then, yeah, there's this funny idea of like sticking in some kind of weird state of light, like a superposition, and realizing a weird superposition where it's fully delocalized and fully localized. Okay, and then, of course, even less baked, back to dough, we can imagine applying an intentionally speckled laser trap across the sample and starting to study things about Anderson localization. So maybe this would be interesting. I'm not an expert in Anderson localization, so but you could control it in 1D. So those are the topics I really wanted to get through. I did promise that I would show you how to make a 10 micron cavity, and this is probably worth seeing because it might be useful to other fields. So this is something that we can do in our lab is take an optical fiber, cleave it, hit it with a CO2 laser, 40 watts. That causes an ablation dimple, and the glass reflows and makes it atomically smooth, like really smooth, a few angstrom, or maybe even less. Which sounds ridiculous, but we know that it's true from AFM measurements, and because we've sent these to a nice coating company and gotten these really nice high finesse mirrors coated on the ends of them, and then we measure the finesse to be 100,000. So it's no problem with good absorption and everything. And then there's no alignment to do after you make this thing. The light is just naturally coupled to the cavity that you can make with this object. So micromirrors, you can make cavities in principle a few microns long. That's one of our goals. We use a 40 watt CO2 laser to do this. And I don't know if you guys have seen a 40 watt CO2 laser, but it sounds like it's not a lot of power, right? Because your refrigerator is like a kilowatt or something, or your computer is 300 watts. But when it's all at one wavelength, this is like a heat beam that you can just aim across the room and nobody can see. Which isn't to say that I do this to my students. But I wanted to show you, like when we first got this laser, it's a pretty impressive movie. We have a target here of cardboard, and this is from a film when we sent a pulse out of this laser, just raw. So the light comes on, it's a blinding flash, which eventually dies out. And then you can kind of start to see the plume here. And at this point, we had to actually, the camera got knocked over by a bus that was passing and started to roll. And we got to do that again. So, okay, that's not real at all. You guys are, I know you understand this. Okay, good. Sorry about that. Again, no sleep. So like this stuff is funny. Okay, so this is the progress we've made. Here's the nozzle of our CO2 laser. This is the last focusing lens. Here's the fiber. We can really nail the center of the fiber. This is the interferometric image. And then we can bring the fiber near a flat mirror. And you can see we can make 5 to 100 micron long cavities, and we get very high finesses. This is all data now. I used my wife as a guinea pig on this project, so she wanted them first. So she did her first coating run for her ND centers in diamond. And now that I know it works, we're doing our lab at 1550. It's working well. So if you need like really confined light that has a strong interaction, let me know. Because this is another hammer, and we can just distribute them because we don't care. We come up and try to make them overlap. Okay, so I guess we're basically out of time. I started a bit late, but I was overloaded with information, too much information. Don't want to put it into this. Okay. Well, with that, then I'll get to the end. There are things we've diamond, locking circuits, cryostats, nanomagnetism, and then these centers. Ask me about this if you're interested. And these are the things I want you to remember. We make really low noise trampolines. We're planning to levitate them and do other weird things. We're actually probably moving most of our stuff to this localization idea. But we're most excited about that. It's easy. It's within striking distance. And then, yeah, coupling right to mechanical treated. I'm not doing any of this stuff. I just write the graphs. This is my group. A day that we went for a hike. And you can actually see my unborn son in this picture. There. Oh, she was there. She was there with us. See, her arm is around her, so it's very believable. Yeah, she just couldn't make it to the hike, so she's just hiding behind the rail. Horrible accident, I guess. Anyway. Yeah, so thank you for your time.
We have a couple questions for the speaker.
How important is it that the cavity is basically vacuum? So in terms of applications, one thing that I could imagine would be pretty exciting if you have that kind of sensitivity is if you think about a quantum gas, it might be entangled. Entanglement, the only degrees of freedom you have would be local pressure variations. And so somehow you can measure pressure variations on the scale of that. You might be able to convert the entanglement in a VEC, let's say. Or you might entangle your trampoline to the entanglement of the gas.
Several people, or at least one brilliant person that disseminated the idea, has come up with this idea. There's a lot of people who are actually bouncing laser light off of a membrane and trapping the atoms with that. And as the mechanical element moves, it shakes the potential. And so you get normal modes that are mixed, and you can address the atoms to control this, or address this to control these. But they haven't done this thing where you have a container of sorts and are looking at it. I guess you're thinking of like a ground state gas in a box. Yeah, I haven't thought of this. I think a good system to do this in might be helium, like with helium, low viscosity would be fun. The Q and the frequency would tell you something interesting, probably.
This is kind of like a basic experimental question. So how important is it that your TEM00 or not in the cavity? So I'm thinking of the distribution of power, right, at the beam waste.
Yep.
So how do you, I imagine you would get different responses, right, if you had different modes in the cavity, or?
Yeah, so we can see all of the modes if we shape our beam so that it exactly matches the emission shape of the TEM00. We get up to 95% or higher coupling. So we can talk to the TEM00 very well, and just by overlap integrals, the other ones by symmetry are not talking. We're not talking to them, but usually in practice we see 95% in the TEM00, and then at a different frequency or cavity length we see the little bumps for the TEM10 and 01. But we can talk to one mode at a time for sure, because we tune our cavities so that the modes do not overlap with each other. And so, yeah.
So you were able to see different responses for different modes?
Yeah. And actually, we've learned to take two of the modes and make them degenerate and have the membrane couple them to each other, scatter them into each other with some rate and lift the degeneracy. And that's how you get that really strong quadratic response, because as a function of displacement, they cross each other and you can avoid crossing. So we've actually started to engineer the modes in this way.
You mentioned it seems like you could use your very, very high Q cavity and then detect the Brownian motion. Right. Does that violate the second law of thermodynamics?
No, No, we do it routinely in our lab. So the way, I think the way to think about this is your laser light is way out of equilibrium.
Yeah, but Brownian motion, you can disorder energy, and then you could turn this disorder energy become ordered optical energy.
So the argument against being able to measure it is the answer to this question of whether if the temperature of a tuning fork and the temperature of your eardrum, a perfect eardrum, are the same, can you hear the Brownian motion? The answer is no. Because the noise emitted by your ear is resonantly absorbed in a way that exactly cancels the reflections coming in. So the spectrum looks exactly white, like Brownian, like you would expect. So you can't see it from this in equilibrium. But if you're out of equilibrium, you would see it. So if the tuning fork was hotter than your eardrum, there would be a little bump on top of that white noise from the extra energy that's being emitted. And in this case, if I get a little bit loose, the laser light can be viewed as an extremely low temperature sensor. So there's a way to map it out there. The noise fundamentally from a laser comes from radiation pressure shot noise, and that low temperature, that's a low temperature hiss. Like it's very quiet compared to the noise of the Brownian motion. Other than that, it would be just equations. But yeah, we're not alone in measuring the Brownian motion. Actually, you don't need a high finesse cavity. We're measuring the Brownian motion with our cleaved fiber just above it. It's a finesse 0.5 cavity or something like that. Just an interferometer can do this.
Now your membrane of your system is not really isolated. You have 4 legs connected outside. Then the outside is supposed to have thermal noise. Would that also affect the membrane? So in a sense, now if you have a laser trap, you can trap an atom because the atom is free. In your case, is your membrane free?
No, it's got those tethers, and I can get back to the force noise measurement here. So if we turn on our fiber interferometer, we measure this ringing at its natural frequency, and that's the Brownian motion. And that is coming from the fact that the chip carrier that's holding these tethers is at a finite temperature, and all those atoms are shaking, and it's a hiss that's driving this thing. And then the membrane likes one frequency, so it responds more. It filters the shaking of the frame atoms.
Any more questions? Let's thank the speaker again.